Welcome to Chapter 6, and in this lesson we're going to be taking a look at functions. We're going to be covering what functions are and how to use them. Also, we're going to talk about testing functions and how to pass data into our functions that we're going to be using on our program. And then we've also got a variety of other associated topics that we're going to cover, such as the accumulator pattern, how to call functions from inside of functions, using a main function. We're going to talk a little bit about composition, and then finally we're going to end the chapter with creating a bar chart using the turtle program. So it'll be a good time. The primary purpose of functions is to be able to allow us to reuse code. So when we're doing something over and over again, a function allows us to call that block of code, and so that way we don't have to retype it over and over again. One of the founding principles of programming is dry, or don't repeat yourself. And basically functions are, it's simply just a named sequence of statements that are grouped together in some logical manner. We consider this grouping of these statements to be considered compound statements. And to write a function, it looks something like this. We're going to have this function here, which is going to be the function header. And it's going to start off with the def keyword, which is short for define. And then we're going to have a name of the function. And then we're going to have a list of parameters that we can pass into the function. So this is what we call the header line, and this is what we call the body. Notice that we have an indent of 4 spaces or 1 tab. In Python, that's how we delineate compound statements or logical groupings. Notice that we can also use these variables that we've passed into the function within the body. Now, compound statements are nothing new. You've seen compound statements before. And where have you seen these statements? Well, we've used them in if statements. So we've had a condition where if something is true, then do a group of text or do a group of statements. And so it's the same thing. There's a couple more bits of terminology that you need to be familiar with when working with functions. So the first one is that the arguments or the variables that we pass into a function, the technical name for those are formal parameters. This is when you are defining the function. When we actually go to use the function in our programming, we call them actual parameters or arguments. And you're going to see a lot where people use these terms interchangeably, but this is the actual technical definition. We have formal parameters, and then we have actual parameters or arguments. When we call the function, we say that it's a function call or an invocation. We are invoking a function. When we're writing a function, we want to make sure that we include a docstring with it. This docstring is going to tell the user of your function what the function does and what the parameters are that it's going to use. And this is to help them understand it, to make sure that they're using it correctly. Now, sometimes it should be pretty straightforward based on what the names of your variables are, but sometimes it's not quite as apparent. So you should always write a docstring to go with each function that you write. Now, within your code, you can access these docstrings for your functions by using this special variable, which is called a dunder variable because it has double underscores. And you can access it by whatever your function name is, dot underscore underscore doc. So remember, everything in Python is an object, and objects usually have different attributes associated with them. In this case, a function is an object, and so we can access its docstring attribute by calling this dot underscore underscore doc underscore underscore. You're probably not going to be using it a lot in this class, but I'm just putting it here just so that way you can understand that you can actually access what this string is while you're actually coding it. So as an example, if we were to call this function and to print out the doc dunder attribute, this is what it would look like. So here we are calling my function and we're passing in hi there and 37. Well, it's going to go up to my function, it's going to print out statement 1 using the hi there, and it's going to print statement 2 with the 37. So you can see that in our simulated output here. And then if we print my function.doc, then it's going to print out what we have in our quotes right here. If we were to call help on our function, you can see what the output looks like right here. And it uses the docstring as part of its help function. So when we call help, it's going to print out your function header, the name and your parameters, and then it's going to print out the docstring below it like this. So again, this is another reason why it's important to provide a docstring, so that way you can actually use the integrated help function within Python. So the question becomes, what happens if we try calling help from the Python shell? Would the following work? So we've seen an example of this before in a previous video, so take a minute and think about whether or not this would actually work. And no, it's not, because we would have to import the module that the function was loaded in. So here you can see import, and then whatever module that we put our function in, we could then call help by saying, well, in this module, this function, and it would return the result. So let's go ahead and take a look at this in our Visual Studio Code. Here I've got a simple module, which is just called E6 or exercise 6_1. And it's just got some simple functions that are just going to add, subtract, multiply, and divide, right? And with their corresponding operators right there. So nothing super fancy, anything like that. But let's go ahead and try to run it in the Python shell to see if we can get our help information. All right. So from within Visual Studio Code, I just hit Control-tilde, which brings up my terminal. And this is just like opening up the command prompt, but the nice thing is that it puts us right in the directory where we're currently working. So if I were to pull up my Python shell and say help on, I want to call help on add, and just call add, well, that's not going to work because I haven't loaded this module into the Python shell. If I try to import it, like we should, and if I say, well, import E6_1, this isn't going to work either because I'm currently in my lecture code folder, and this file itself is actually loaded within my Unit 3 subfolder. So I have a Unit 3 folder within my lecture code, which is where this file stands. So there's a couple different ways that we can address this. The first is we could say, well, import Unit 3 dot E6_1, and now the module is imported. So if I try to run help now on add, it's not going to work. It's going to say it's not defined because this has to deal with the scope of the function. In order to get the help, I would have to say, well, help unit 3 dot E6_1 dot add. Now it will actually pull up the help on the function. So that's okay. Okay, we have access to it where it views unit 3 as a module and E6_1 as a submodule, right? Or unit 3 as a package and E6_1 as a module. But there's some better ways to do this. One way is that we could exit out. We could change directory into unit 3, then load Python, and then import E6_1, and then we can call help. But this time we have to say E6_1 dot add, and there we have it. So we cut out the unit 3 bit, right? So that's one option. What if we don't want to change directories? Well, we can go back into our Python from our root directory, in this case, my lecture code folder, and we could say import unit 3 dot E6_1 as. We can use the as keyword to relabel this. So now I could just say, like, we're just going to call it test, right? So now I have this new alias, this new name for this bit right here. So now I could just simply call help, help on test.add. And so there you can see that I've relabeled this bit as test. So that makes it a little bit easier, especially if you have unwieldy package names, like in this case module names. E6_1 just doesn't roll off the tongue very well, right? So I could say import this as maybe test isn't a good name because it's not very clear, but like I could say underscore, I could call it MM for my math, or I could say my math, right? So now I can say, well, give me help on mymath.add, and it works the same there. So you've got quite a few different options. I just kind of wanted to walk through how the various import statements work. But the key thing to realize is that all of these import statements, like import this unit as, this works within your code as well. So you don't have to just do this just in the Python shell, right? So if I go ahead and exit out of my shell, let's take a look at how I could use this module in another program. Now that we've seen the help function loaded within the interactive shell, let's go ahead and see what it looks like if we run it in a source file. So here I'm going to pull up E6_1B, which is just a driver program which is going to import my other file. So here I've got E6_1, which is the previous file we looked at, and here is my driver program. Now if you'll notice right here it says, hey, this couldn't be resolved because right now we are currently in the lecture code folder and unit 3 is a subfolder. This is a limitation of their particular linting program I'm running within Visual Studio. The one I'm running is called PyLint. And so this will still work. This just comes up as a warning. But because these two files are in the same directory, this import statement will work with no problems. If I run the code right here, you can see it executes it exactly how it's needed. My IntelliSense, which is like when I hover over this, it will tell us exactly what we're looking for. Normally, if right now you can see that it's highlighted with yellow as a warning. So to fix that, all I could simply do is just open up the unit 3 folder under lecture code, and now it will find it with no problem. And the nice thing about this is it also gives us additional information. So you can see if we hover over our add, it tells us exactly what the function does, which is a really nice feature of the IDE, is it tells us based on the doc strings that we provided. So if you read it, like for example, subtracts the second operand from the first. That's exactly what our doc string says, and that's where it's getting that information from, right? Subtracts the second operand from the first. Op1 is the first operand, op2 is the second operand. If I go back to this folder and hover over that, it tells us exactly what it does. So that is the beauty of using doc strings within your code, because eventually you're going to get to a point where you don't remember 100% of what you wrote. Okay. Now, if you're looking at this wondering what the arrow none is, that's the return type, and we're going to talk about that in just a little bit. So, but for now, I just wanted to show you how you can use the help function within your program if you wanted to. But if you're using an IDE like Visual Studio, you don't even have to call help because it comes up when you just hover over the function that you have typed in. So, but if we go ahead and run it, you'll see that we're going to get all the various outputs as we would expect. So here we get from lines 14 through 16, we get help on our add function, and you can see it prints out our doc string, and then it actually prints out what we told it to print out, 3 plus 4, and that equals 7, right? And then we do the same thing for help on module, or on the subtraction function, same thing with the multiply function, and same thing with the division function. So that's just showing you the power of it. So if you get these yellow squigglies up here on your import statement, again, so like right here, I'm going to go back to lecture 3 because I'm in the lecture code module, but folder, but my module is in my unit 3 subfolder. You can see now it says like, hey, we can't read this module. So it's not going to give us the additional information that we're looking for when we hover over it. So like, Just want to be clear, when you see these yellow squigglies on your import statements, check your folders where you've got it loaded, because that's probably the biggest problem that you're looking at. One final thing that I want to say about this is you may not have these errors at all. It depends on what linting service you have set up within your IDE, and that's beyond the scope of this class to troubleshoot. So I just want you to be aware that if you have yellow squigglies like this on your import statements, it's probably has to do with the way that your IDE is set up or the linting service that you're using. So I wouldn't worry too much about it, but if your code isn't actually executing when you hit run, then it's something to worry about. Okay, now that doesn't go for all the code. Like if you had red squigglies down here saying this variable hasn't been defined, that's a legitimate error. But like the case of this right here, it says, hey, I don't have this unresolved, or I've got this unresolved import. That's just because it's the particular language server that I'm using. So in my case, what I would do is I would just simply change directories to unit 3, and that way it solves that problem and I can get the full linting that I need. All right, so again, troubleshooting these types of problems are beyond the scope of this class, but I just want you to be aware of it in case you see it. Now, getting back to the real content of this chapter, we have to deal with functions that return values. And what are we talking about when we're saying that they return values? Well, in Python circles, a function that returns a result is referred to as a fruitful function. And here's an example of one such fruitful function. Here you can see we have a function called add, and it is going to return the result of operand 1 and 2 being added together. When we return the result, we're not printing it out, we're not doing anything, we're sending it back to the part of the code that called this add function. A function that doesn't return a result is referred to a procedure or a non-fruitful function. And so an example of this is what we saw in our previous example that I showed you, where we have add and we simply print out the result of operands of 1 plus 2. So again, this is a procedure or a non-fruitful function, and this is called a fruitful function. So we call this return the return statement. And functions always terminate after a return statement. So if we had a function that was written like this, this print function would never get executed. It is unreachable code because the function would always terminate after this line right here. So if we were to take a look at our code that we had before, you can see that we have all of our print statements. Let me get rid of the directory. So you can see our print right there, print right here. So these are non-fruitful functions. Here is the code that's modified to be a fruitful function. So here you can see we have a return statement at line 15. Again, here's a return statement. So now this won't print out the result. We would have to do something with it. So how would we do that? Well, let's take a look. What happens when we return something? So if we pull up our driver program again, here was our original driver program, and instead of importing E6_1, we're going to import E6_2, which was this one right here, where we're actually returning the result. Now, when we execute this block of code and we add these two together, we won't see the result, okay? But what we can do is we could say, I want to set this equal to variable x1 is equal to. Now, what's going to happen is this function is going to get called. It's going to add the result to these two things, and it's going to store it in variable x1. Okay? Or what we could do is we could say, I want to print the result of this function. Right? So if I comment out all of this other help stuff, right? If I comment out my, whoops, we're not doing C++ or Java, we're doing Python. So if I comment out all these helps, right? Help. We're going to comment those out. And now if we run the program, we should only see this line, actually, the results. These other ones, you're not going to see the results. So here you can see 3 plus 4 equals 7, but we don't see the results for either of these operations because we are performing the operation, but we're not doing anything with the result of it because we are returning it versus printing it out. So here you can see our original file, we're printing out the result. Here we're just returning the result. So if I want to actually do something with these, I could say, well, okay, I'm going to store this, let's see, I'm going to store this result in x1 just quick naming purposes. I'm going to store this in x2, right? And I'm going to store this in x3, right? Now, what I could do is I could actually move this code up to the line before it. We're going to cut this out, move it up to the line before it. And same thing with this one, right? Now what I want to do is I want to add in another variable, and I can say, we're going to print out that, and we're going to say, give me the result of x1, right? Actually, what we can just do is we can just do this and just change this. Oops. So now we got x2, and now we've got x3, right? So now we can see the results of these operations because this result is stored in x1. Okay, so now you can see here are the results. We could also take it one step further. Instead of storing this result in an intermediate operation, we could simply say, well, I'm going to just take this function right here, I'm going to get rid of this, and I'm going to paste it in here. And the same thing with this right here. I'm going to cut this part out, and I'm going to get rid of that variable. And now we've condensed our code and made it a lot more streamlined. Okay. So now if we run it, you can see that we got the same results. So you don't have to store the result in an intermediate variable. We don't have to store it in a temporary variable. We can use the output of one function to immediately feed the input or an argument to another function. And this is kind of a concept that a lot of new students to programming can get easily confused on, and sometimes it makes the code a lot harder to read. So if you're not comfortable doing this, for now, definitely use intermediate variables to help keep track of the results of your various operations, okay? So I'm just going to restore this to its original state because I'm going to use it again in class. But I just wanted to show you that it is possible to use the output of one function to the input of another function. For those of you that are pursuing a degree in computer science, or you're going to go on to be a developer or a software engineer, unit testing is something that you absolutely have to embrace as a core part of your job. You have to be able to write tests that will validate that the function that you wrote is correct, or that it is working under certain set of conditions, and if those conditions change, then it will lead to a error in your unit tests. So it's absolutely critical. It's an integral part, right? And the basics of what we're doing is we're going to write a test that's going to call the function given certain inputs when we know what the expected outputs are going to be. So for example, if we write a function that adds two numbers together, right, say we will give it 2 plus 2, and we will test that the function returns 4. And we will test it with a variety of different inputs to make sure that we're covering weird circumstances, right? What if we give it a string of 4? What if we give it a -4? What if we give it 3.99? There's a lot of different ways, and you can take an entire class on unit testing and writing good tests. This is more just to get you familiar with the concepts of unit testing and what you're doing. Now, within Python, there are some test frameworks that you can use, with the major ones being unit test and PyTest, right? So I'm introducing these as just kind of familiarization for you, so I highly recommend that you go and check these out. But for this class, we are going to use just a very, very simple test framework called test. All right, and it's nowhere near as comprehensive and as valuable as what unit test and PyTest are, but it has simplicity, and that's essential for what we're doing right now as an intro to programming. So we are going to use the test framework as an introduction. Let's take a quick look under the hood to find out how this test module actually works. So here we have a singular function called test equal, where we pass in an actual value, an expected value, and an optional places value that if we don't include it, it will automatically be set equal to 5. And what it does is it first checks to see if the expected value is a float. And if it is, this part just checks to see that the difference is less than the number of decimal places that we specified. So if we have 5 places, then it's going to be less than or equal to 0.00001 off, right? So if it's not a floating point number, then we're going to check to see if the actual is just equal to the expected. So this works for like integers or strings, things like that. So we can actually test to see whether they're exactly the same. If this passes, if the floating point value passes, it'll print pass and then return true. Or if it is not a floating point number, it will do the same thing. It will print pass and return true. If neither of these two situations pass, and remember it's going to be either or, it's not going to test both, then we will print out that the test failed, indicating what was expected and what we received as the actual value. And then it will return false. So that's the test method, test equal, and that's part of the test module that's going to be available on Canvas for you to download and include in your directory where you have your Python module that you're going to be writing. So to use this test framework, we need to make sure that we have it saved in a test.py file. And then we simply import it into our code using import test. For now, I want you to just simply keep a copy of this test.py file in the current directory that you're working, just to make things easy and to make sure it's easy to find. Let's take a look at how we would actually use this file. So here you can see we're importing the test module, and we're importing this extra module that we're using for our math functions, and we're importing it under the alias myMath. We're then going to call the test equal method of the test module, and then we're going to pass in as the actual value the result of adding 5 and 5 together using the add function that I created. Then we are going to give it the expected value of 10 because we know that 10 or that 5 plus 5 should equal 10. So we're passing this value in as the expected value, and we're passing in the result of this function call or this function invocation as the actual value. And then we're going to run it. And this is what the output's going to be. It's going to be pass. So we're going to call this file and it's going to call pass. Right? So here is, again, we're going to import the test. This is the file that we're going to be using as part of our driver program. So this right here is our driver program. And then, of course, we're importing myMath as, we're importing E6_2, and we're just renaming it for the purpose of this module, right? And then again, this is the actual value that we're passing in, and this is the expected value. When we're writing unit tests, we want to make sure that we're picking values that are good test cases, right? So how do we go about doing that? Look at these two examples. Do you think that these are going to be a good set of test cases to test out our math function or our add function? If so, why? Well, I can tell you that they are not a good set of test cases because they are the same equivalence class. That means that they don't really test anything differently, right? We've got a positive number and a positive number, and we are testing the second case with another positive number and a positive number. We can be pretty sure that we're not going to get any different results based on these two test inputs. I mean, other than the expected value, right? So you can think about it this way. If we were to look at x and y as our input space, where the first one is x and the second input is y, and z is our output space, you can see that our test 1 is in the same quadrant as our test 2. So we shouldn't expect to get any different results. Now this gets much more complex when we're talking about 3 and 4, 5 different parameters, but when we're looking at just simple 2D space, then we can represent the output as a third dimension. And so right then and there we can see that this is probably not a pretty good test case. Here's some guidelines that you should follow when you're writing test cases. So number one, you have to have some knowledge about your expected limits. Is there a upper or lower limit that you should expect? You also want to make sure that your inputs are between negative and positive infinity. In this case, since we're testing 2 inputs, we want to make sure that we are checking our values for both our first and second input, or our x and our y. So this means that in this case, our boundary is really 0. That's really the only different place where we can expect different results. So what that means is that we should test a negative value, a positive value, and 0. We should check something that's on the boundary. But we should do the same thing for our y values, our second input as well. We should check negative values, positive values, and 0. So this is going to result in 6 different equivalence classes. And we also call this boundary value analysis. And that just means that we're looking at what are the logical boundaries of our outputs expected to be, and how can we pick different inputs to get a result that's in those different equivalence classes. Now that we covered unit testing at a very high level, mind you, let's go ahead and return the conversation back to talking about some more of the peculiars of dealing with functions. And let's return to our discussion of scope. If you remember this chart right here, scope refers to the level of visibility or lifetime that a variable has, right? So any variable that is declared inside of a function is local in scope to that function. That means that if we try to access the variable outside of the function, we won't be able to because it no longer exists. Formal parameters are defined inside of a function. So you can see right here, op1 and op2 are formal parameters. These are variables that are local in scope to the add function. So we can use them anywhere inside the body of the function, but once we leave this function, these 2 variables no longer exist. If you remember from our previous discussion, global variables are those that are declared outside of an enclosure. And as I mentioned, that it can be really easy to mess up a program and introduce really hard to find bugs by using these global variables. And so you should use them with caution when you are doing any non-trivial programming. In this example right here, you can see that we have both a global and a local variable, right? The local variable here is op2 because it is declared inside of this add function, where op1 is a global variable because it is declared at the global state. And we can use both variables inside of the add function, but we cannot use op1 outside of the add function. Now I know I've been throwing around terms, global, local, and closed, and it can get kind of confusing. So let me try to clarify a little bit more, especially the enclosed part. Any variable that is not global or local is what we'd consider non-local or enclosed. So in this bit of code right here, you can see that x is local to the add function, but in this one, x is not local because we have this other function right here. We have defined a new function called func, and x is not a local variable, but it is enclosed within the add function. So x is local to the add function, but it is enclosed to this function right here, just called func, right? It is not a global variable because it does not exist at the module level. So we declare it inside of the add function, so it's local to add, but it is enclosed to function. Now, variable y is local to this internal function, so func, and so you cannot see y in the add function or outside of the add function. As soon as we exit func, y is going to go away. X will stay there until we leave the add function, at which point x will go away. And the only variable that will be left is op1. It's important to remember this because we need to know how the interpreter is going to look for what the value of a particular variable is defined as. Because we have, what as I mentioned before, we have shadowing, where you have a global variable declared and then we use the same name, like say x or I. It usually happens with loop indexes that they don't overwrite the value, but when the Python interpreter is looking at your code and you have this variable that says, x is equal to 7, and then you later use x, it's going to use the most local option available to it. If it doesn't find a local variable x, it will then look at its enclosed variables. It will then look at its global variables, and then finally, if it doesn't find x, it will look at the built-in variables. So it's really important to understand how the Python interpreter is going to resolve what the value of these variables are. Chapter 6.5 talks about the accumulator pattern. What is the accumulator pattern? Well, it's just having a variable that stores some value, and we iterate over a set of things, and we update the variable with a new value. We are accumulating new data, right? So we would also often use the accumulator pattern when we were keeping track of a sum where we are adding a bunch of values together. And each time we iterate through the loop, we are adding a value from something into the sum, and so that sum is going to accumulate in values. So let's take a look at an example of the accumulator pattern in practice. And there's all kinds of different patterns in software engineering. This is just kind of like a very easy introductory one to make it easy for you to understand the concept of patterns. So in this file, we are combining your knowledge of functions, and we're returning back to our illustrious turtle class to do some drawing to help you understand this. So here we are importing our turtle module, and we've created a function called drawSquare, where we're passing in t and we're passing in sz, right? And these are examples taken from the text, so I don't want to get hung up on this, but I would probably choose better variable names, right? I would probably say that this might be turt or turtle or something like that. And size, we could say, well, let's actually just spell this out to be size, because it's not, sz is kind of lazy, and a lot of programmers are lazy and they like to use the minimal amount of characters possible to represent something. But for a student, it can be hard to follow sometimes. But in this case, we simply have a drawSquare function that we're passing in t and sz. So let's go ahead and expand our docstring to make it a little bit better, right? So here I'm going to go ahead and hit enter, and then I'm going to hit enter again, and t is simply a turtle, and sz is distance the turtle will travel. So now it's a little bit more apparent what sz is, right? And if we look at the code, we are going to loop over 4 things. So we're going to basically right here, we're going to draw a square that each side is sz in length, okay? And that's it. So now we have this function called drawSquare where we're passing in a turtle and the size, and it's going to draw a square. So now we get to the main part of the program, because remember, we're just defining the function. We're not actually using it, or we're not calling it yet, or we're not invoking it yet. So we set up our turtle and we set up our screen, and then we give the turtle some start positions, and we give it a starting size and a space, right? So now for x in range 20, so we're going to do this 20 times, we are going to move the turtle to some location minus some distance. So space is how much space we're going to have between each of our squares. So it might be a good idea to go ahead and add a comment to this to indicate that. Say space between squares. So now it's a little bit more easy to understand. Like we'll add another comment here, starting size of square. And now we get down into our loop, and so now our size is size plus 2 times the space. So this right here is our accumulator pattern in practice. We have one variable size, and every time we iterate through the loop, we are going to be adding 2 times space to the value of size. Then we are going to lift up the pen for the turtle. We're going to go to our start location, and then we're going to put our pen down, and then we're going to draw our square. And that's it. So let's go ahead and see what this looks like when we run it. And there you have it. It did exactly what I said it would do. We started off with the size of 4, and then once it was done, we added the 2 times the amount of space to each side, and then we located to the new starting point, drew another square, and we just repeated this 20 times. So let's go ahead and change this. Just maybe we won't do it 20 times, maybe we'll only do it 10 times, but we'll change our starting space to say maybe 4. We'll make it more tightly packed together. And now you can see that the squares are a little bit smaller. We can do it again. We could say, well, you know what? Let's make our space, let's make them really spread apart. So here you can see the power of functions and not having to repeat ourselves. We can simply call or invoke the one function over and over and over, which is what we're doing right here on line 36, and we just pass in the new value. Here we're using a singular value, size, to store what the current size is, and then we're simply doing a calculation to update it. We are accumulating a bigger value. So that's the accumulator pattern combined with functions in one nice little program that lets you play around with drawing squares. Another thing that's important to remember is that we can call functions from other functions. Functions can even call themselves in a process which we call recursion. We often use functional decomposition to break a large problem into smaller subproblems. So you might have a task that needs to be done, and you might call a function to execute this task. Well, within that function, it might call 4 other functions to do smaller components of the piece of that problem. We can also take a specific case and generalize it to make it fit a larger set of problems through what we call generalization. And let me show you an example of what I'm talking about. Here we have a function called drawRectangle, in which we are giving the function a turtle, we're giving it a width, and we're giving it a height. Rectangle is the general case, and we also have a more specific case of draw square. Here you can see that we have a generalization where squares are rectangles, but they're a specific thing. So we can have a draw rectangle function, but then we can also call a draw square function that simply invokes draw rectangle, passing in the value of the side for both the width and the height. And this is an important skill to be able to recognize when you can have a function that can be generalized so it can cover more applications than maybe the specific one that you are trying to implement. So let's take a look at this in the code again. So here I have a program that will draw a polygon. So that's the generalized problem, right? But here we have a specific application. We want to draw a square, so we simply call draw polygon, where we pass in the length and we pass in a turtle and we pass in the number of sides that we want to draw. Here is another specific application where we draw a circle, where we set our circumference equal to a certain value, and we say our side length is equal to this circumference divided by 360, and then we draw a polygon with 360 sides, right? So it is not a true circle, but it's a close approximation of it. We could even make this a little bit smaller and say, you know what, only draw 180 sides. And then, of course, the rest should be familiar at this point. We're setting up a turtle, and here we're calling draw square and draw circle, both of which are going to rely on the generalized problem, which is the draw polygon. So let's go ahead and run this and see what it looks like. So it drew the square pretty instantaneously, and now it's drawing the circle, which is really just a polygon with 180 sides. And you can see how we used one function in two different ways. I previously talked to you about the flow of execution in how Python, or how the interpreter, goes through and reads your code. And it does so sequentially. It does one line after the next after the next. However, this process is interrupted through control structures such as loops and if statements. When the interpreter encounters these quote-unquote detours, it will go and it will process those structures individually and then return to the original program at the point of where they were called. It's important to remember that inside of these structures, inside of the if statements, and inside of the loops, that those structures themselves are still processed sequentially. So it's not really any different, but they just introduce a kind of like I said, a detour off the main beaten path. So let's illustrate this. So here we have our main program, and we're going to execute it from top to bottom. But we might also have these functions that we're going to call. So when the main program encounters this sub1 function, it's going to go to this function, execute whatever's in this function, and return to the same point in the main part of the program. We might have another function called sub2 that calls another function. We're going to call it sub4. So the main part of the program is going to go and it's going to start executing sub2 sequentially, and then it's going to encounter sub4, and it's going to execute sub4 sequentially, and then when it's done, it's going to return to sub2, and then when sub2 is done, it's going to return to the main part of the program. And then we might have another function called sub3, which will do the same thing as sub1. And then the main part of the program will finish out. Now, in this illustration, we have what we call the main function, the main block of code that gets executed. And we haven't really talked about how you create a main function within Python. Well, every Python module has a special dunder variable called name, which is really underscore underscore name underscore underscore. If we are running the module directly, that is, we are in Visual Studio Code and we are executing this module here, right? This module's name will be set to main. However, if the module is imported by another module, then its name will remain the actual name of the module. So we can create a main function in our program and call it like this. What this is basically telling you is that we have a main function declared here. We are defining main, and we're doing something. And then we simply, inside of the module, we have this bit of code that says, if name is, quote, main, the dunder name main, then execute the main function. So remember that if the module is run directly, the name will be set to main. So if we are running a particular module, then it will automatically set its name to main, and therefore this condition will be true, and we will execute the main function. So this is a little bit more confusing than some other languages like C++, where you just have a main function. Or in Java, you have a main function. This is kind of a workaround within Python to have a quote-unquote main function. So here I have a modified version of our turtle program that we looked at earlier. And you can see that in it, instead of having this code just sitting out there loosey-goosey in the module, I've embedded it inside of a main function. And now, in order to call it, we added this line of code right here. It says, if name is equal to main, then call the main function, which is going to execute this block of code right here. And this is a good practice to get in the habit of because we don't want to declare variables in the global space if at all possible. If we look at this version of the program, you see we have all of these global variables just hanging out right here. And we really want to avoid that because at any point we could overwrite our poor Speedy turtle and he might meet an untimely demise. However, if we have Speedy inside of our main function, then Speedy is local in scope to main, and we can't necessarily modify him through some other function unless we pass Speedy as needed. So in this case, you can see we're passing Speedy around to these various functions. So Speedy, when we call draw circle, he gets passed into the draw circle function. So there we have a copy of him. Well, we don't have a copy, we have a reference to him. And so we can access our turtle. If he was just hanging out in the open, in the global space, anybody that was running this could modify Speedy. When I say anybody, I mean any function could modify Speedy in ways that we didn't necessarily intend. So this is a good way of practicing defensive programming by making sure that you put your main function in your module and make sure that you include this block right here to make sure that now we are encapsulating all of our variables in a enclosure. They're inside of a function, so they're not in the global space. They're not global in scope. The final thing that I want to talk to you about is an important concept in software engineering, and that's the concept of composition. When we build functions that call on other functions, that's essentially what composition is. We are making up something that consists of a lot of other parts. Let's look at an example of how the book is using composition. So here we had this previous diagram where we have our main method and it's calling different functions, right? And this is an example of composition. We are using these different functions together to solve a problem. So in the textbook, we have something very similar where we have a main function that is calling various other functions. We have the print function, which is then calling area2, which is calculating the area of the circle based on given coordinates. But these individual functions don't really need to know that. In this case, the distance function is calculating the distance between 2 points. Area2 is using the value that is returned from that as an input to the area function, which calculates the area of a circle based on a radius. So you can see that we have two functions that are solving their own unique problems, and then area2 is composed of those two functions to solve a larger problem, which is calculate the area of a circle given 2 coordinates. So to recap, why do you care about composition? Well, it allows you to leverage different components to solve a particular problem, and it increases usability because you can use these individual components for multiple things. It also makes it a lot easier to maintain your code because you can make small changes to one section of the code and not necessarily have to worry about messing up a lot of other stuff, right? Maybe you have a new algorithm to solve a particular problem, and it returns a result in the same format, so you can just modify this small section of code without breaking the rest of your program. And it's a core component of object-oriented programming, which we're going to talk about more in a little bit. Let's look at one more example of composition at work. So here I've got my module, and we're going to be drawing a bar chart using our turtle class. So let's start at the top. Let's start in our main method. And I say at the top, but remember, we are encapsulating our program into a main method by using this bit of code right here. So if we're running this module directly, it's going to automatically execute the main function. So here we have our main function, and we are creating a list called bar data. Well, we're going to talk about lists later, but this is just a notation for creating an empty list. We are then going to create 10 bars of random size between 0 and 100. And we're going to, whatever that value is, we are going to add it to our bar data. Then we are going to set our maximum height to whatever the highest value of our bar data is. So we're using this max function, which is a built-in Python function, to figure out how tall does our chart need to be. We're then also calculating our number of bars based on the length of bar data. So if I change this value right here, this numbers will automatically be updated. I then set a border size, create a window, and set my world coordinates based on the border size and my max height variables. And I also set this background color because why not? I then call initialize. So I set up my turtle. Notice here that I'm not calling turtle.turtle with a capital T. I'm instead calling this initialize function. So let's come up here and see how I'm initializing my turtle. So here I have initialize, and I'm creating a turtle called turt here, and so this is what you're used to seeing. I'm then setting a color blue, I'm setting my fill color red, I'm setting a pen size, and I'm setting a speed, and then I'm returning our turtle to the main part of our program here. So we talked about how when we're executing the code, calling function jumps to different places within our code. So that's what's happening. We are going to the initialize function, we're jumping up here, we're going to execute this block of code, and we're going to return it here. Now another important thing to remember is that we are setting my turtle equal to whatever this turtle is. So we are passing the reference. So I could call this turtle something else. I could call this turtle Bob, and it wouldn't matter because as long as I use Bob elsewhere in the program, then everything will be okay. So like in this case, this still says my turtle. Well, I need to change this to be Bob now. So now for each bar in our bar data, we're going to draw the bar, and we're going to pass in Bob, our turtle, and bar, which is the size of the bar that we need to draw. So here, now we jump up to our draw bar function, and we are going to begin fill, which is just going to simply fill in the polygon that we create. We're going to draw our bar, and then we're also going to call label bar, and we're going to pass in a height, and we're going to pass in a turtle, right? So in this case, turtle here is just is Bob, but here you can see that we have renamed Bob T. So T within this part of the code is whatever turtle we pass into this draw bar function. So it's important that you as a student keep your head wrapped around what variable names are what and what's actually happening. So just to reiterate, we've created a turtle, and here the turtle's called turt. We returned that turtle, and we've set Bob equal to that turtle. So turt and Bob are the same turtle. We then pass Bob into the draw bar function, and so we come up here, and T is now actually Bob, but we've just given it a new name. So here, this is really like Bob begin fill, but that wouldn't work because Bob is a variable that's local to our main function. So this is just doing the same thing, and we're going to then pass Bob, which is now T, into our label bar, and this is just simply going to write some values on top of our bar, and then we're going to finish off the rest of the bar, and then we're going to end fill, which is going to shade in our bar for us. At that point, we are going to return back to the main part of the program, and in this case, it's simply going to just draw the next bar in the loop, and the next bar, and the next bar, and the next bar. So let's go ahead and see what that looks like. Go ahead and make it a little bit bigger here. So there you can see where it drew the labels on top. Let's actually just go full screen with it. So there you can see, and the font's a little small, but you can see that it generated a list of values and it labeled each bar at the top of the bar based on its size. So we can go ahead and we can also run it again. And we can change some values here. Here we can say, you know what, I want 20 bars, and I want them to be between a value of 0 and 300. So here we're running it again, and you can see the graphs being built from a random value of 0 to 300, and we're doing up to 20 bars. So this shows you how I used functional decomposition to break my problem up into smaller parts. I've got a part where I initialize my turtle that I'm going to use. I've got a portion of my code that I use where I label each bar, and then I have a portion of the code where I have the ability to draw a bar. And then the composition part of that is the reverse. It's combining all of these various functions into a program that actually makes sense. This is a skill that takes practice and time to nurture, and you will get better with time as you think more programmatically about problems that you're given. How do I break this up into the smallest components to make it easier, and to not only to test, but to be able to write your code one small section at a time rather than being overwhelmed with the larger whole. It's much like writing a big essay for an English class. Do you just start off and just write, or do you think about what you're actually writing first, break it up into an outline? I've got these main points that I want to talk about, and then here's my supporting details. Programming is much the same way. You think about the larger movements of your code. What are the big things that have to happen? And then you think about, okay, how do I execute each small part of that? So that's composition in a nutshell. It gets much deeper and much more complex, but this is just looking at it at a very high level in an introductory way, so that way you can be exposed to it and be familiar with it when you see code that's structured this way out in the wild. So that's it for Chapter 6. Like always, if you have any questions, don't hesitate to reach out. I know this chapter, there's a lot more going on than the previous chapters, so it's okay to be confused with certain topics, but the important thing is that you reach out and get help as early as you can, so we have time to go over maybe one particular concept or another that you might be a little bit more confused about than something else. So good luck, and let me know if you need anything else.